Anyways, okay. Last time we talked about the unit cell. We have different parameters that we keep track in the unit cell. What are those parameters again? Yep, length and angles, and that basically can describe the shape of the unit cell, no problem. We're going to use those lengths and angles to classify them in different crystal classes eventually. However, we talk about crystals being infinitely long, or we model them with infinity. So when can we consider something infinite on the atomistic scale is the question we're going to ask. So crystals, are crystals truly infinite? No, because you can pick them up, you can see them. If they were infinite, they would take up the whole universe. They're not. So they are finite. While unit cells extend to infinity. Is it safe to approximate that a unit cell is a real crystal then? That's a fair question, right? Because if we're using this model and we're trying to explain something we're seeing, is the model actually valid to talk about our observation or not? Okay, to do that, let's consider a cube of copper. Copper is my favorite metal. Has a volume of 1.00 millimeters cubed. How many unit cells will fit in this volume? That's an easy way to look at it. Easy. Okay, let's analyze this question. What are we looking for? Yeah, it's going to be a dimensional analysis problem. And we're asking how many unit cells, right? Okay, tell me important information. Size of the unit cell. Oh, we don't have that. Got the cube. What else is important? Copper. Words matter here. I know, it's terrible. Okay, so Aiden, you were like, we need the unit cell volume. Okay, so how are you going to find that out? Yeah, look it up. You can import it into Avogadro. You can look it up in different tables. I looked it up into a table. And at 293 Kelvin, because the lattice vectors do depend on temperature. They will change with temperature. Do they change a ton? It's on a system-by-system case. But we're just going to go with this temperature. Cu has a lattice vector of 3.6147 angstroms. Yeah, I love math. That I got to give Katie some physics in this class too. A bunch of chemistry, terrible. Yes. So let's draw the unit cell of this thing. Joe, you got to stop clicking that thing. Okay. We don't know this yet, but we will figure this out eventually. The copper has a face-centered cubic structure. So let's draw in our coppers. It's a cubic, so what does that mean about each edge? They're all equal. So all the lengths are the same. And then what were you going to say about the atoms, Lily? Yeah, one in each corner. It's face-centered cubic. Yep, an additional 6, which makes that way more confusing. And now, Katie, you asked the question, you were saying something about the lattice vector. The lattice vector, Jesus, is just the length of that unit cell, right? So what is the length, this distance from that atom to that atom? Yep. Okay. Lily, you mentioned something about this unit cell. And remember, this is a face-centered cubic, which we really haven't defined yet, but we'll get there. The word cubic, what is that going to mean? Yep. So what's A equal to? Yep. What's B equal to? Yep. What's C equal to? Yeah. Okay. So we can use that information to figure out our little tiny crystal of copper, that little bit. Does everybody have a good idea too about like what that looks like? Like 1 millimeter cubed. Small, really tiny. Like you couldn't, like that dot, it is 3-dimensional, but it's hard to see that it's 3-dimensional. Okay, what now? Yeah, let's do that then. Okay, so you want to convert these into millimeters then, right? Okay, so 3.6147 angstroms. We got to do some sort of conversion. What units got to go in that denominator? Angstroms. Okay, I don't know the direct conversion to millimeters. You might. I want to go to meters. Okay, for every 1 meter, any idea of how many angstroms? Yep. Okay, now, what units got to go down here? Yep. What unit's going up top? Yep, 10 to the what? Yep. So multiplying that through, I actually didn't do that math out all the way, but we could do it pretty well. That's what I see. Is that right for others? Okay. The fun part about planning approaches is rarely do students take the approach I take, so we kind of do it on the fly and hope we end up at the right answer. Okay, can I erase the rest of this question? Okay. Woo! All right. What now? So we want to cube it. We could do that. Why are we cubing it? Right. What property are we trying to get to right now? Yeah, volume. So volume would be that cubed. We can take this value, 3.6. Wait a minute. Yeah, we're good. Never mind. I got scared. We're fine. -7. millimeters. We got to cube that thing. Somebody crunch that number for me. Make sure my number's correct. We're going to try. I have. Oh, I can absolutely do this on my phone. Yeah, that's what I got. And what's the unit on that? Yep. Yep, that's how I do it too. Good sig fig usage too. All right. Now, okay. So now I will preface this. We drive home sig figs a lot in general chemistry. Here, if you're close, I'm not going to knock you. However, we do know the unit cell volume to this level of precision, though. Okay, like it is very crazy that we can know something that small. We'll talk about why we know that through Bragg's law and the Lowy equation later. Okay, what now? We have our unit cell volume in millimeters cubed. Yeah. So we know our crystal is 1 millimeter cubed. We know we have this many cubic millimeters for every 1 unit cell. You divide that through, I found 2 times 10 to the 19 unit cells. Okay. Is that a big number? Do people have an idea of the magnitude of that, or do we want to do something additional to that to determine the magnitude? Okay. So do we want to do another problem with this number, or do we understand that this is a huge number? What was that? I don't know what you're even saying. Okay. So we're good. So can we represent a unit cell and describe a real crystal? I think so. I think this justifies it. It seems valid to me. Okay. Any questions about that one? So we're going to use unit cells from here on out because we've done a justification that, yeah, it should work well for a crystal, a real crystal even. Okay. But I used the term face-centered cubic, and we really didn't talk about that yet. We talked about it in general chemistry. That was a while ago for most people. And even so, that's probably in the section that you were just like, this is going to be one question on the ACS exam. I don't care about it. Or you just memorized however many atoms fit within a face-centered cubic versus whatever. So why do people like crystals?
Because our brain sees patterns.
Yep, our brain sees patterns. They think it's cool. I like the shiny factor to things. But the symmetry. We're really weird creatures where we favor symmetry. The things that we consider the most beautiful in nature, or even like in other partners in some cases, tends to be symmetry. The prettiest faces tend to be the ones that are the most symmetrical. Let's talk about symmetry. We had earlier, we said we were going from like more basic or less information to more information, and we had like a hierarchy. Do you guys remember what that hierarchy was? Yeah, whichever way you want to go. Yep. And that led to what?
14 Bravais Lattices.
Yeah. Then that led to 32. Which leads us to
230 space.
I don't know why I capitalized that P, sorry. Okay, yeah. So when we look in Avogadro and we look at real crystals or ones that we can imagine, we need to have an idea of what it looks like to really understand what's happening in that system. And then if we want to model those systems to eventually talk about their electron density or their wave functions. Okay, so we're going to rise through this way. We're not going to go over every single 230 space group, but we're going to talk about the symmetry elements contained in those. Okay? All right. There we go. Here. We're going to hand some stuff out. We'll go from less complex to more complex. Yeah. Actually, there is a book you can buy associated with that. I don't think there's a need to. You can find it online. If you go into crystallography, you'll probably want to have those crystallographic tables, space group tables. Okay, so I handed a handout to you guys with the different crystal systems. Let's talk about the 7 crystal systems. And remember, we're starting at a point where people weren't really sure if matter was made of small particles or not, and we're going to get to the point where it is, and we can talk about the individual atoms. This classification is based upon the unit cell metrics, but it's technically also based upon symmetry of the unit cell parameters. If you look in that table I've given you with all those unit cells, is there a single atom indicated in there? No, there isn't. This is about the lattice parameters. We're not considering the atoms really right now. Technically, it can be based on symmetry, though. Okay, you have this table already, but we're going to kind of go over what's sort of in this table and talk about the crystal systems and some changes that we have. So we're going to build the table in our notes. You'll probably want about, I don't know, I have about half of a page for this. Another thing we're going to talk about sometimes is point symmetry. I'm just seeing that you can actually see that. Yeah, you can. We'll use point symmetry and volume symmetry in some cases. Point symmetry, we're actually talking about a physical point. Okay. Translational symmetry, where you can move through things. We'll get there. Okay, so what are the 7 crystal systems that we have? Yep. Yeah, I want to name them all. I want you to know those names too. Yep. Yeah. We're going to start with triclinic and go to monoclinic, and we'll follow a pattern that way. So we've got triclinic. Triclinic crystals tend to be the most common crystals. What do you know, or what does the table say about triclinic systems in terms of their axes? Is there any symmetry restriction? Okay, what about the angles of the cell? Yep, all different. And then the max symmetry you can have as a 1 bar. That's not going to mean anything to you quite yet, but when you look back at your notes in about a week, it will.
Was
Mhm.
with the zeolite?
Zeolite
Was
was not.
No, not that. I mean,
I can't remember what the angles of the zeolite were, so I'd have to look at that to remember. I think it's either hexagonal, trigonal, or it would be orthorhombic.
I remember the angles were usually 290.
Oh, we actually, 2 of them were equal, yeah, so it might have been tetragonal. Okay, what can you say about the symmetry of triclinic systems? It's garbage, there's very little. If you had to solve a crystal structure, do you want to see triclinic? No, because there's no symmetry. It's tough then. We can do it. It's just tougher. Okay, then we have monoclinic. Is there any restriction on the lengths? Right, none. What about the angles? Yep, alpha and gamma have to be equal to one another, and does it say a length or a angle? Yep, you got to be 90. So if alpha and gamma are equal to one another, but they're not 90, it doesn't mean you're still not at a monoclinic. Maximum point symmetry is something called 2 over m, which again won't mean much to you. It has to deal with rotational symmetry. So 2, C2, if you're taking inorganic, and then the m is a mirror plane. You don't know what I am even saying, we're going to talk about those things. Okay, then we have orthorhombic. Is there any length restriction? Yep, none. And then when we get to angles, what do we got there? Yep, bless you. They're all equal and they're all 90. Higher symmetry, MMM, there's mirror planes. Yep. Tetragonal. What do we got there for a length restriction? Yep, A is equal to B. What about the angles? Yep. They're all equal to 90. Okay, and then 4 over MMN is the point symmetry, which again, I'm sorry, has to deal with a 4-fold rotational axis and then some mirror planes. Trigonal. Trigonal and hexagonal sometimes can fall into one another, or you can reduce them down to each other. A is equal to B. Does it give you an or? One, two, three, four, five, six, seven. That's interesting. It's not on there. Trigonal. You have rhombohedral, which, yeah. All right, we'll have to reconcile that in a little bit. But we won't worry about it right now. Yeah, because trigonal sometimes gets wrapped into hexagonal, and I think we can, I think what they're considering, what is it, rhombohedral, can actually fall into trigonal. Okay, angles for that one. Alpha has to equal beta, which is 90, and gamma is equal to 120. Or we can have this other restriction, A is equal to B, which is equal to C, in which case alpha is equal to beta, which is equal to gamma, but there's no angle restriction. That seems to meet, what is it? The rhombohedral that they have there. 3 bar M is there. We have hexagonal, where A is equal to B, alpha is equal to beta, which is equal to 90 degrees, 26 MMM. And then the last one we got is a cubic. Cubic's easy enough. What do we know about the lengths? Got to be all the same. A is equal to B, which is equal to C. And what do we know about the angles? All the same, and they're equal to what? Yep. This has a lot of symmetry. M, 3 bar M. Okay. I'm not going to make you memorize these numbers and angles and things. But what I do want you to be able to do is look at a picture similar to that table and say, what is the crystal system? Okay? Yes.
Where is that 120 degree angle? Because it looks basically the same as if it's just orthogonal, just bigger.
Yeah. Looking at it, it kind of is. I will have to investigate that one more. I think this unit cell picture that we have in here is wrong, so I will find a better thing for you guys. Okay? I'll come with a better printout so you can see it. The other thing is with your daily problem, I'm going to have you go in and actually physically look at the models that we have in the Chem Lounge and find ones that match. Okay? Any other questions right now? Okay. These work fine for the lattices. But what about when we have more lattice points and we have some atoms incorporated in here? That's going to change things up a bit, and we can actually introduce more symmetry elements. So we're going to ask the question, what about atoms / more lattice points? If we incorporate more of that, we get more symmetry. Once we get more symmetry, we can introduce the Bravais lattices. So this next handout is a better handout than the one you've currently received. Man, Joe, you're having a tough go. Or just put your phone on top of it. There you go.
It's not that funny.
It's pretty funny.
It is funny.
No, it's not. You know, sometimes that's just where my computer's gonna die with that neighbor.
So in this new handout, it gives you a better idea of what we're looking at when we start introducing some atoms or lattice points. These tend to just be elemental in nature. We can look and start incorporating some ionic systems, but if you look, there's more classifications there. If we check out the cubic system, what are the 3 different Bravais lattices we have for those crystal systems? Or excuse me, for those Bravais lattices? Yep, we got simple, body-centered, and face-centered. So let's talk about those. What are their meanings and how are they a bit different? It will be more common in this class to refer to the Bravais lattice than it will be the crystal system. And again, it's more important to be able to represent the picture than know all the symmetry requirements. Okay. With the Bravais lattices, we can have different types of centering. So what are we going to put in the center of our unit cell? Okay, what are the different types of centerings from that series of pictures that you can see? Mm-hmm. So simple also gets called primitive. And we're going to give it the symbol P. What else did you say, Joe? Yep, base-centered. We didn't talk about that in Gen Chem.
Oh, no, I think you mentioned it and said you don't care about
What are the other centereds? Yep, face-centered. That's the last one I'm going to put down. And then what's the last one that we didn't put in? Yep.
Is there a reason why you're putting it in that order?
I like it that way. I don't know why I like it that way, but I just like it that way. Okay, so basically we introduced how many new symmetry operations? 4. How many crystal classes did we have? Or crystal systems, I'm sorry. 7. How many Bravais lattices do we have? 14. Where the hell does that number 14 come from? Because if we have 4 new symmetry operations, we had 7 classes, right? Yeah. So question. Why are there only 14 Bravais lattices? Shouldn't there be, how many did you say, Joe? Yeah, 7 times 4, 28. Right? So why do you think there aren't?
We're non-conducive to those.
Well, I was thinking about this.
When you say non-conducive, what do you mean?
Well, let's look at X.
Some of the ones that have less symmetry, are they not? Are they not gonna be?
Yeah, they can't be any of the other ones, right? So the ones with low symmetry are just stuck doing what they're doing. Right. So that's part of it. There are some that are just flat out prohibited by symmetry of the system. So you're right there. So 1, some are prohibited. That's not how you spell prohibited, is it?
You're missing an
Missing
I
an I.
between that H and B.
Okay, there we go. Another example is, so you were talking about low symmetry systems. I'm going to talk about a high symmetry system. Body-centered can't exist for a cubic lattice because it will just end up being one of the other ones. Or it just, actually, because of that point symmetry, what do we have to have? We had to have M3 bar M, which means it has to have that type of symmetry. You can't have a base centered with that type of symmetry. It's just impossible. So base centered cannot exist for a cubic lattice. And earlier I said a lot of times some of the others collapse into one another and they're made redundant. Like you could have this type of centering, but then it just turns into one of the other ones. So we just kind of group them together that way. So symmetry makes some lattices redundant. And do you know what I mean by that when I say redundant, or no? Yeah, identical. Yeah. Okay. However, writing out like face-centered cubic, body-centered cubic, that just does a lot of writing. There are shorthand conventions, and the one that we're going to utilize is Peterson's convention. Do they use that on here? They don't, but you can look up in other tables and other things to see this. So we're going to use the Pearson symbols. As a shorthand. That is our example. Let's go with orange and green. My hands are a mess. chalky hands. Actually, I like the feeling of chalk on my hands, but I don't like how I get it everywhere. Okay, I write that on an exam. What the hell does that mean? Okay, intuitive. Some crystallographers are in the room. Okay, so orthorhombic. That O, why is the O orthorhombic?
Because it starts with O, and it's the only one that starts with O.
Yes, orthorhombic starts with O. If you look at the different Bravais lattices, that's the only one that starts with an O, or in terms of the, what are they, the crystal systems. So this is orthorhombic. Okay. And then the F. Yes. Let's say it were a primitive orthorhombic. What would the symbol be? OP. Overpowered. Yep. Okay. Does anyone see a problem with this, though, looking at your table? T's.
Try, so would it be a 3 or would it be R?
Ooh. So, we got a lot of T's. So alpha is used for triclinic. Okay. You might be asking why an alpha? How the hell do you get that out of a T? It's related to the word anorthic. What other T's are we going to run into? Tetragonal. And what else?
The other one we wrote down.
Yeah, the other one we wrote down on the other page. It's not actually in this thing. Yep. H is used for both trigonal and hexagonal. Yep. And they sort of collapse in on one another in most cases. Okay. So now, we're going to use those symbols a lot of times throughout the class to describe different systems we're looking at. Next time, we're going to move to the 32 crystal classes, which we introduce more symmetry elements. So we add in more atoms, and we talk about mirror planes, glide planes. Actually, I'm sorry, that's for space groups. But we'll introduce rotational mirror planes and inversions and something called an improper rotation. Okay. Joe, question. Anorthic, I don't really remember the definition off of the top of my head, to be quite honest. But what I remember from it is it's something about like unequal.
3 is not equal.
Well, yeah, triclinic though, no symmetry.
There it is.
Is tetragonal T?
Tetragonal is T.
Okay, cool.
Yep. Other questions? Yeah, Katie?
This picture, in my opinion, isn't very intuitive. Like body center, is like that's ugly.
Yeah, it is really ugly.
Well, that's fine, but like these two, I feel like should be switched. Is that just something you're gonna like?
Sort of.
Oh my god, why is this?
It will be when, that's why the things I'm going to give you are going to be like Civ files that you can look on Avogadro and visually rotate and inspect them. Or I will like have physical models like I brought in the other day or I'm going to make it so it is not complicated. I am not going to hand you something on an exam that's like, this is hexagonal. Hexagonals are horrible to look at. Or like, for example, a body-centered orthorhombic. I might indicate that that's what the crystal structure is, but it most likely won't be very important to the overall problem.
The pictures are fine. The names seem unintuitive.
Yes. And in some cases, like for example, this one is called simple. And if you look, I would consider that one, which one was it? Yeah, base-centered. So, and also sometimes the names are synonymous. It's like naming aquarium fish. They have like 12 different names, but they all mean the same thing. I'm not going to knock you if you're right in describing that name through what you know. Does that make sense? Okay. Any other questions?